Hello everyone, welcome to MakeUnions channel. In this video, I would like to teach you a special case about fins when there is negligible heat loss from fins tip or to be adiabatic. I will draw equation for temperature distribution, heat transfer rate, efficiency and effectiveness. If you are new here, welcome. In this channel, I will teach mechanical engineering lessons like engineering mathematics, heat transfer, and fluid mechanics by illustrating their concept and application. If you like these kinds of videos, I will be delighted by tapping on the subscribe button and notification bell to get recent uploads. Fins are used to enhance heat transfer rate from the plane wall. Consider a fin, a rectangular fin having cross-sectional area of AC, which is for rectangular W equals W times T, and a perimeter of 2 times W plus T. Under steady conditions, by using energy balance and Fourier's law and assuming cross-section and thermal conductivity of K to be constant, we obtain differential equation governing heat transfer in fins that equals d2 of T over dx2 equals HP over Ka times A times T minus T of infinity or environment. In order to make it easier, we consider some changes in variables. As HP, K and A all are constant and positive, we suppose M2 equals HP over Ka. And for temperature variation, we have theta, which is equal to T minus T of infinity. If you take a derivation from each side, with respect to x, we'll have d theta over dx equals dt over dx. And this is a constant and its variation is 0. Again, if we have another derivation, we will have d2 theta over dx2 equals dt d2t dx2. If we substitute in our main formula, we will have this d2 theta over dx2 equals m2 times theta. That's our new differential equation. This equation is a linear homogeneous second order differential equation with constant coefficients. So the characteristic equation will be lambda to the 2 minus m to the 2 equals 0, which lambda will be plus or minus of m. Okay, the answer of differential equation equals theta equals C1 e to the plus mx plus C2 times e to the minus mx. C1 and C2 will be evaluated by appropriate boundary conditions. First boundary condition is temperature at the fin's base. X equals T of fin at x equals 0. The second boundary condition may be specified to one of 4 different physical situations. that we conclude the adiabatic finitives. T of fin at x equals L. By applying appropriate boundary condition, we'll have T of x equals 0 is T naught minus T of infinity, which will have theta naught equals T naught. It's our first boundary condition, BC1. Our second boundary condition is dt over dx at x equals L is 0. We had dt over dx equals d theta over dx. Again, this will be 0. If we substitute our first boundary condition in the temperature distribution equation, this is temperature distribution equation, we'll have theta naught equals x equals 0. We have x equals 0, C1 e to the 0 plus C2 e to the 0. Then we have C1 plus C2 equals theta naught. And for the second boundary condition, we should take a derivative from temperature distribution equation. We have d theta over dx equals C1 m e to the ml. This is our second boundary condition, minus C2 m e to the minus ml. By solving double two-dimensional equation, we will obtain C1 and C2. These two, this is the first equation, this is the second. We'll have C1 equals theta naught e to the m minus ml over e to the ml plus e to the minus ml. And C2 equals theta naught e to the ml over e to the ml plus e to the minus ml. This is our constant coefficient of this differential equation. This main differential equation. If we factor out the theta naught and make a common denominator, we'll have theta over theta naught equals e to the ml plus e to the minus ml e to the minus m times L minus x. It is equal to this minus ml minus x will be positive, and plus e to the m times L minus x. And if we divide numerator and denominator over by 2, we'll have theta over theta naught. I just added here. It will become hyperbolic cosine's formula, which will be cosine, hyperbolic cosine of m times L minus x over hyperbolic cosine of ml. This is our temperature distribution as theta and theta naught. For getting the main formula as T and T naught, we'll have T equals T infinity plus T naught minus T infinity times this expression hyperbolic cosine of m times L minus x, or hyperbolic cosine of m times L. This is the equation. For evaluating heat transfer rate through adiabatic tip fin, we use Fourier's law of heat conduction. We had temperature distribution equation that was theta over theta naught equals hyperbolic cosine of m times L minus x over hyperbolic cosine of ml. We should differentiate theta with respect to x. Theta d theta over dx equals minus m theta naught hyperbolic sine m times L minus x over hyperbolic cosine m times L minus x. At x equals 0, we'll have d theta over dx, and consider it to be hyperbolic tangent, we'll have minus m theta naught hyperbolic tangent times ml. For heat transfer rate, we had Q equals minus Ka d theta over dx. And then by substitution, Ka theta naught m in this become plus m hyperbolic tangent of ml, and we open up the m, which was sq root of hp over ka. Q will be sq root of hp ka times theta naught times hyperbolic tangent of ml. That's it. Our heat transfer rate through adiabatic tip fin. Okay, for the fin efficiency of adiabatic tip fin, we'll have a proportion of actual heat transfer rate from the fin over ideal heat transfer rate from the fin if the entire fin were at base temperature, and we show it by eta of fin or eta of f simply. In the limiting case of zero thermal resistance or infinite thermal conductivity, which K reaches to infinity, we'll have the maximum heat transfer rate, which will have Q equals integration from 0 to L at base temperature. This is T of B, base temperature, and this will be T of B, entire will be T of base. H P d of x times theta, this is A, this is A, and if we substitute T equals T naught and theta theta equals theta naught we'll have, and it will comes out of the integration L equals HP L theta naught. This is our maximum heat transfer rate. For the adiabatic tip fin, we had Q equals square root of HP Ka times theta naught hyperbolic tangent of ML. If we substitute these two terms into our formula, this formula will have Q equals SQRT of HP Ka theta naught hyperbolic tangent of ML over HP L theta naught. We will have Q equals hyperbolic tangent of ML over ML will be simplified and make this formula. This will be our eta of fin. As the formula shows, eta of fin has a reverse ratio with ML, and we have Ka over HP times 1 over L. As the Ka of fin is bigger and H of environment is smaller, and the ratio of perimeter over cross section to be smaller, the efficiency will increase. This bigger, this is smaller, and this is smaller. Or H over P, A over P bigger. One assessment of fin performance may be made by evaluating the fin effectiveness. It is shown by epsilon F, or epsilon of fin. That is the heat transfer rate of the constant base temperature over heat transfer rate that would exist without the fin. For the heat transfer rate without the fin, we had HA T naught minus T of infinity, which will be HA theta naught. And for the with fin, for the adiabatic fin tip, we had with fin adiabatic SQRT of HP Ka theta naught hyperbolic tangent ML. And if we substitute to our main formula, epsilon of A and adiabatic will be Kp over HA hyperbolic tangent of ML. This is our formula. Okay, for the notes of fin effectiveness, we have the formula that was epsilon has a relativeness of Kp over HA. As the K is bigger, H of environment is smaller, and P over H ratio is bigger, the effectiveness will increase in number. So we should install the fin at the environment which has a lower H. For instance, in a radiator of an automobile, water is flowing inside the tubes and air passes outside. And we should install the fin at the outside because H of air is smaller than H of water. And another note that you should remind, its effectiveness must at least be 2. It's the lower limit of effectiveness. Okay, as the first example, I brought you this one. A turbine blade made of a metal alloy, K equals 17 watt over a meter Kelvin, has a length of 5.3 centimeters and a perimeter of 11 centimeters and a cross section of 5.13 square centimeters. The turbine blade is exposed to hot gas from the combustion chamber at 973 Celsius and with a convection heat transfer rate of 538 watt over square meters times Kelvin, and the base of the blade maintains a constant temperature of 450 Celsius and the tip is adiabatic. Determine the heat transfer rate and tip temperature. It is obviously said that tip is adiabatic. Okay, there are 4 assumptions to solve this problem. 1. Heat conduction is steady and one-dimensional. 2. Thermal properties are all constant. 3. Heat transfer by radiation is negligible. And 4. The cross-section of turbine blade remains uniform. We write down our given data. K equals 17 watt over m Kelvin and H 538 watt over square meters K, and perimeter is 1.11 centimeters and AC equals 1.13 times 10 to the minus 4 square meters. This is also in meters. Okay. Firstly, we calculate the ml, which was in our formula. M was SQRT of HP over KA times L, which will be H 538 times P 0.11 K 17 times A 5.30 times 10 to the minus 4 L, which is a 5.3 length 5.3. It's clear. 5.3 times 10 to minus 2. This will conclude to 4.36. It doesn't have a unit. Our heat transfer rate through the blade is equal to SQRT of HP KA times theta naught, which is T of infinity minus T of blade times hyperbolic tangent of ML, this value. Okay, we substitute our values H was 538 times P 0.11 times K 17 times 513 times 10 to minus 4 times T of infinity, which is 900 hot gases 973 minus 450 times hyperbolic tangent of 436. If we give this to the calculator, we'll have 376 watt. The temperature distribution for adiabatic tip is equal to T of x minus T of infinity over T of base minus T of infinity equals hyperbolic cosine of m times L minus x over hyperbolic cosine of ml. T of L equals Tb minus T of infinity over hyperbolic cosine of ml times plus T of infinity. If we substitute our values to this equation, we'll have Tb was 450 minus 973 over hyperbolic cosine of 4.36 plus 960 Celsius. A hot surface at 100 Celsius is to be cooled by attaching 3 cm long, 0.25 centimeters diameter aluminum pin fins, which has thermal conductivity of 237 watt per meter Kelvin to it, with a center to center distance of 0.6 centimeters. This is as it's shown in the figure. The temperature of surrounding medium is 30 Celsius and the heat transfer coefficient on the surfaces is 35 watt over a square meters times Kelvin. Determine the rate of heat transfer from the surface for a 1 meter times 1 meter section of the plate. Also determine the overall effectiveness of the fins. There are 6 assumptions to solve this problem. 1. A steady operating condition exists. 2. The temperature along the fins varies in one direction only. Normal to the plate. Heat transfer from the fin tips are negligible. 4. The heat transfer coefficient is constant and uniform over the entire fin surface. And 5. The thermal properties of the fins are constant. And the heat transfer coefficient accounts for the effect of radiation from the fins. A figure from the side view has been shown here. And for these kinds of problems, firstly we should find the m value that we have defined before. M equals SQRT of HP over KA or ASC, it doesn't differ equals its perimeter equals PD. D is our diameter over KPD2 KPD2 over 4 equals, if we bring it up, will be 4H over KD. And we substitute values. 4 times 35 over K, that is 237 times 0.25 times 10 to the minus 4. If we solve this calculation, we'll get to 15.37 inverse meters. It has m to the minus 1. And so we have the value of m, and L also is known. The length of the pins is 3 centimeters, so we can find the efficiency of pin. We have eta of pin hyperbolic tangent of ML, hyperbolic tangent of ML over ML equals, we have the values and we just substitute in our equation. L is 3 centimeters. It will be 0.03 meters. This will conclude to 0.93 or simply 93%. It's a high value for efficiency. The number of fins and finned and unfinned surface area and heat transfer rates from those areas are the following. N equals 1 square meter over 0.0006 times this number again equals 27,777, and number area of fins will be A of fin, this number times PDL pi DL, pi DL plus pi d to the 2 over 4 equals D equals 0.0025, L equals 0.033 100, and again D equals this number. You will get to, if we calculate this value, equals 6.68 square meters. Next step will be area of unfinished wall. It will be 1 minus 27,100 times we should cancel out the surface of fins, which was PDL. If we do this, we'll get to, and do the substitution, we'll get to 0.86 square meters. And the final step is to find the heat transfer rate of fin area. Q of fin will be eta of fin times Q dot of fin, which is max, whenever it is max. Q of fin if it is max, or ideal maximum, equals eta of fin times H, A of fins, heat convection coefficient times A of fin times T of base minus T of infinity. We'll get to, if we substitute 0.935 times 35 times 6.68 times 100 minus 30 will result in 15,300 watt. And Q of unfinished will be A of unfinished H times A of unfinished times T base minus T infinity. If we substitute, we have 35 times 0.86 times 100 minus 30, that will conclude to 2107 watt. You see that this is a smaller value. Okay, then the total heat transfer from the fin plate becomes this: Q of total fin, I use it, the summation of these two, 1300 plus 2107 equals 17.4 kilowatt. The rate of heat transfer if there were no fin attached to the plate would be this: A of no fin. It is obvious that will be the plain valve, and it's just no fin. We have this layer, we consider without fins, that is 1 meter times 1 meter equals 1 times 1 square meters. Q of no fin will be Q of no fin, H times A of no fin times TB minus T of infinity. 35 times 1 times 100 minus 30 will be 2450 watt. And then the fin effectiveness becomes epsilon of fin. Its formula is Q of fin over Q of no fin. Q of fin over Q of no fin, which is 17,400 over 2,450, which will be 7.1, and it's bigger than 2. That was our limit, and the fins are effective in this problem. I hope it was a helpful video. I will be happy if you share this video with your friends. If you have any question, let me know in the comment section. I will answer them as soon as possible. Thanks. See you in the next video. Goodbye.